Hello, everyone, and welcome to today's webinar, Power Design Pro Live. Today, we're going to show you how to use the most powerful generator sizing tool on the market. By the end of this webinar, you can expect to become familiar with how to enter motor loads into PDP, how load sequencing impacts generator size, steps versus groups within Power Design Pro, entering building preload, an example with a fire pump, mechanical design capability of Power Design Pro, and how to get additional help and support information. I'm your host today, Laura Unger, Industrial Manager here at Generac Power Systems, and I'm going to go over a few logistics for today. There's a question box that you can feel free to use at any point throughout the webinar. There will be a live Q&A session towards the end of the webinar where we will answer all of those questions. Secondly, I want to let you know that you'll be getting an email tomorrow with a post-event link to the recording of this webinar. And in that email, you will also have a link to sign up for Power Design Pro. It's free registration there. With me today, I've got Michael Kirkner. As always, Michael, thank you for being here, and I'm going to shoot it off to you right away.
Well, thank you, Laura. So are you enjoying your Halloween?
I am. It's been spooktacular.
Oh, you all can't see this, but the ladies that are running the AV here are all dressed up in costumes today. So Power Design Pro is a program to size generators to the electrical loads and do some mechanical design work as well. You can access it a few different ways. I listed the link, or you can just Google Generac Power Design Pro and it'll pop right up, the first search in Google. I have a little link here that I'm going to use. Power Design Pro, the first time you open it, will ask for a registration. You have to put in some basic information and then it'll remember it from that point forward. So we're going to come into Power Design Pro, and the first thing I'm going to do is start a new project, and I'm going to name this webcast. And hit save. And then it'll open up a project. You click on that project, and now you can put multiple solutions in that one project. So I'm going to start a new solution, and I'm going to say sizing example, so I don't have to do any typing. And in this particular case is the basic setup page for your project. So altitude, elevation, voltage. There are some limitations here for transient capabilities. I normally keep those initially opened up to the maximums. You can always come back later and set them from 100% to 80% loading or a specific voltage dip. But I'm going to also show you some other ways we can look at doing some sizing in which we take manual control as well. The reason why I like to keep them relatively open is if I set it to 80% load, you're not going to see a solution that would be at 81%. And you might find that that actually is closer in line with what you desire. Standby duty, we're going to start off by doing a diesel solution. Regulatory constraints, we're using US EPA, which is product for North America. And this is just some general information that's shared within the program. It's not used for sizing. So I'm going to start by hitting save. And the first thing it's asking me to do is to put in a load. So we're going to put in 3 motors to start off with. So let's put in a motor load. Motor number 1, I'm going to make a 200 horsepower. And I'm going to put it in step 1. So as I enter that motor, it's an across the line start motor, and it's going to draw about 1200 SKVA, and the kilowatt hit on the engine is going to be about 300. So I'm going to save that. So we have the first load in. Now I'm going to add a second motor, which is going to be a 100 horsepower motor. And I'm going to put that in step 2. So I'm setting up in this first sequence, basically starting the motors largest to smallest. And then we're going to enter a third motor. Add load, and let's enter a motor. and we're going to put it in step 3, and we're going to make it a 50 horsepower motor. So 3 motors, a 200, a 100, and a 50. And the sequence we're using is largest to smallest, all across the line. In doing that, we find that the program is going to pick a 350 kW diesel genset, but it's going to put an upsized 500 kW alternator on there to create some voltage stiffness so we can stay above a 35% voltage dip tolerance. In this particular configuration, if we go above the 35% voltage dip, a NEMA motor starter is going to drop out. So it really doesn't give us any extra capability. If we wanted to narrow that voltage dip down, I could go back to the automatic settings and I could put in a smaller voltage dip and it would automatically size it for a smaller voltage dip. Or I could come in here manually and simply see, do I have a bigger alternator at my disposal? For the 350, we do not. So let's look at a 400 kW node. So instead of automatically sizing, I'm going to manually pick some size product. So if I size it with a 400 with a 600 alternator, my voltage dip came down to a 25% voltage dip, giving me a little more headroom for some NEMA motor starters. The next thing I'm going to do is switch this back to auto. And notice we started off with, if we start with the biggest motor first, we're actually going to get the smallest sizing solution. However, that may not necessarily be most real world, because if a big motor starts, at some point it's going to shut itself off and cycle, right? It's going to start and stop and start. So at some point that big motor is going to want to come back on, and most applications don't want to shut off the other loads prior to bringing a big motor on. So in the real world, the sequence of this is a little different. The real world, typically the biggest load has to come on last. So let's change that to the order such that we bring the smallest on first and the biggest on last. When we do that, we see that the size of the generator bumped up a little bit. Now we're dealing with a 500 kW generator to be able to handle the hit of starting that 200 kW last. If we put them all in the same step, we're going to get a starting in which we're starting everything concurrently. In that particular case, the size of the generator is going to jump up even larger, where we've got a 600 kW diesel, but an upsized 800 alternator end on there. In the real world, we think that the second scenario that we did probably makes the most sense. Natural sequencing naturally occurs in buildings. Things rarely all start concurrently. So we created some load types called groups within Power Design Pro. And if you put all of your loads into a group, the group is going to assume non-concurrent starting. And it's going to assume the loads naturally sequence, but it's going to assume the biggest load is going to come on last. And when we look at putting them all together in a group, we find we get the same solution that we had when we sequenced them with the biggest load coming on last, which is basically a 500 kW. The other thing Power Design Pro does really well is it allows users to enter some building preload, like off your peak demand charge. So I'm just getting rid of some of these loads for right now. And I'm going to show you how to maybe enter that. So you go to your peak demand charges, you get a year of billing history, and you say, my peak load on a given application was maybe 200 kilowatts. So I'm going to put some preload on the building, preload, or I could call it peak demand charge, demand charge. And if I want to put in 200, I could just simply enter 200 kW like this. But if I do that, I'm actually creating kind of a false condition. It's basically bringing 200 kilowatts of load on all at one time. You can see the 200 start kilowatt hit here. That's probably not what's going to happen. You're going to initially close in with the transfer switch, and you're going to have some lighting, and then the building's naturally going to come back to life, HVAC, any of the larger loads in the building. So a different way to enter this load would maybe be 20, or let's say 10, 20 kW load steps. In that particular case, we're still getting 200 kilowatts of running load here, but the hit for any one is only 20 kilowatts. So let's add that, save. So right there, a 200 kW diesel would be loaded at 100%. Now I could put in a loading limit, or I could manually select a bigger node, but I want to couple another load with this. I'm going to actually add a second load. Now I want to add a fire pump. So let's add a fire pump. Fire pump right there. And let's make it a 75 horsepower fire pump. And I'm going to put that in group 2. So when a 75 horsepower fire pump starts, I'm going to start, worst case, I'm going to bring it on across the line. And a 75 horsepower fire pump starting across the line is going to draw 450 start kVA. So that's going to be a pretty big hit on the genset. And fire pumps have a requirement per code to limit the voltage dip to 15%. So let's add this load, save. And we're seeing we're going to need a fairly large generator to handle that big hit and keep a 15% voltage dip. So you got a 400 kW diesel with a 600 alternator to manage that voltage dip less than 15%. A lot of fire pumps don't start across the line though. So let's edit that. A lot of fire pumps use Y delta starters, one of the starting methods. So let's go reduce voltage, Y delta. In using a Y delta starter, that SKVA that we were looking at comes down. Instead of 450, it's now 281. And if I hit save, what we're going to see is the size of the generator came down some too, a 350 with a 400 alternator. I didn't need so much alternator stiffness because the Y delta starter reduced my start kVA a bit. Now let's go back and edit that load once again. We have a unique feature in Power Design Pro called motor load type. So if I come in here and if I assume that Y delta starter is on an application where the motor's unloaded, it's some sort of diverter valve, some sort of clutching mechanism, some mechanism by which the motor can get to full speed on reduced voltage. Basically, it can stay in Y start all the way up to speed. Then we can plug in a relatively small SKVA number. If that motor is on an application with high torque, where it transitions very early before the motor can accelerate, we're going to have to treat that motor as if it's starting across the line because the transition is going to happen so early in the acceleration cycle of the motor. We think a fire pump lives somewhere in between. It's low torque at start, but the torque builds as the motor accelerates. And at some point, the fire pump motor runs out of torque and has to make that transition. Hopefully, we give it a good 5, 6, 7 seconds to push as high in speed as it can and make that transition up at 75, 80% speed. And now we get an SKVA hit somewhere in between those two settings. So this is some knowledge that's built into Power Design Pro. A lot of the competitive programs in the market only assume unloaded at start, and they use this much lower number. And we don't think that's very real world. A fire pump typically cannot get up to speed fully on basically Y start. The other cool feature of Power Design Pro, so I'm going to put it back to where we started there, is we have these load shed capabilities within the program. Oftentimes when you're mixing a fire pump with optional standby loads in the building, you don't want to run them both at the same time. In the case here, you may want to shed off the optional standby circuit, the building, when you're running the fire pump. In this particular case, shedding off that load brought the load level way down, but I still needed the big generator because I had to still be able to start that fire pump. So let's come back and let's actually change the starting method of the fire pump to something that's going to be a little more easy on the genset. So I'm going to do edit. Let's change that Y delta starter to a soft start. So now with a soft start there, you may take a look and see that the SKVA still is up there a ways, But if you notice, the soft start is set up currently for a voltage step. Now, soft starts can be programmed a couple different ways. It can be designed to just immediately jump up to its current limit setting, and then you're going to get a fairly high SKVA number. And it's not giving you much sizing relief if you got to hold a tight 15% voltage dip. So let's set the soft starter for a nice voltage ramp. So instead of stepping up to the current limit, it's going to ramp up to it. And let's set the soft starter for a relatively low breakaway voltage. Now that we have a low breakaway voltage, we're not going to be hit with a very high SKVA. And when we do our sizing, save, if I shed off the building, we can find that we could have started that fire pump with a much smaller generator now. So what we can do is do an either or. So in this configuration, to run the fire pump, I need an 80 kW with a 130 alternator. Or I could run the building and not the fire pump with a 200 kW, but that would be loaded at 100%. So you're probably looking at more like a 250. So you can see by putting a soft starter in here and by making a decision to shed off the building when you're running the fire pump, assuming this is optional standby and not emergency system loads, you can find that your sizing can change dramatically by using some of these features. The other thing I'm going to show is, let's take this, this fire pump and let's look at the last way we could potentially power it is with maybe a VFD. So I'm going to edit the fire pump and I'm going to change the load type from a soft starter to a VFD. When we look at a VFD, VFDs are basically rectifiers on the front end, and we assume that it's going to be a noisy rectifier and have about 30% current distortion. That's a typical 6-pulse 3-phase rectifier. And when we assume that current distortion of 30%, we're going to pick up a harmonic current spectrum that we're going to apply to the generator. Now, if that's a better device, if it's maybe 12 pulse or filtered, let's pick filtered, the harmonic current distortion goes down and the distortion harmonics go down as well. So let's start here with just an unfiltered 6-pulse rectifier, save. We find to power that, we're going to need a 100 kW genset with a 200 kW alternator to keep our voltage distortion in check. There's full harmonic analysis within Power Design Pro. So there's these tabs on top. If I want to see what that looks like, I can go to harmonic analysis. And I can actually get a feel for what my waveform is going to be like. This is a mathematical representation of this harmonic voltage distortion that we're getting as a result of having that VFD on a 200 kW alternator. If we wanted to see what it looks like if we downsize that a bit, we could come in, and if I bring it down to a 150, you can see the waveform is getting more and more distorted. And at some point, we're going to enter the land of dragons and monsters in which we have problems. 13% is probably still workable, but as you get up to 15 and 18, you're expecting problems. So we normally like to try to keep it down in that 12 or under %. If we need to on a project, 13 is probably kind of more a cutoff point. So we have full harmonic analysis capabilities in the program. The other thing we have in the program is full documentation. So clicking on the documentation tab, you can bring up the spec sheet for a generator. So I can open up a spec sheet and actually see the spec sheet for a given generator. Or I can look at install drawings or spec text. We also have tools for mechanical design for exhaust piping and gas piping. Right now I have a diesel, so we can't see the gas piping. So let's convert it over to a natural gas gen. So I've converted it over to a natural gas 130. And if I go into gas piping, I can size my gas piping. I'll put 100 feet of piping here. Oh, 100. And it tells me if I want to run my gas piping 100 feet, I'm going to need about a 3-inch pipe. and that'll give me 0.18 inches of pressure drop. So if I say, hey, what if I did a 2.5 inch pipe? What's that going to look like? You can manually come in, pick a 2.5 inch pipe, and you notice you just missed the 0.5 inch water column mark. So that's why it dropped that as a solution, but very valid. It really wouldn't need a 3-inch pipe. A 2 would work. And a 2.5 would work. If you try to go smaller, you get down to a 2-inch pipe. Now you start to see your pressure drop starting to build, 1.2 inches of pressure drop, and you're starting to lose a little bit more of the pressure. If you get to a point where the pipe is obviously way too small, you're going to drop all your pressure in the pipe and you're not going to have any left for the generator. So there's full mechanical design capabilities for exhaust piping and gas piping in the tool as well. Just one or two other things. There is help capability within the program. Clicking help here will bring up a PDF file that you can get all sorts of background information. You can contact us. There's an email as well as an 844 number to communicate with one of our sales engineers here at Generac for supporting you in your application needs. You can also email the project. So I can share the project. I can simply type in an email, click on the project and put some notes, and I can send this project to somebody at Generac or your supporting distributor out in the field to be able to take a look at the project and put another set of eyes on it for you. So it's very easy to share projects as well. Power Design Pro is free software. It's loaded on our corporate public website. You can find it through the link I provided, or simply Google Generac Power Design Pro and it'll bring you right to the Power Design Pro tool.
Thank you, Michael, for going over how to use Power Design Pro. At this time, I'm gonna invite the audience to put any questions they may have into the question box, and we're gonna go ahead and answer them for you. I know there's been a lot that have come in throughout. First one that I see is, how do you model the elevator regenerative power in the software?
So elevators are available in two types, hydraulic and cable. The hydraulic elevators are basically a soft starter, which we have a load type for. The cable elevators are basically a VFD. Power Design Pro sizes for the VFD and its harmonics. However, it does not make a check on regeneration. So Power Design Pro assumes that you're going to have offsetting loads in the load list to absorb the power of a cable elevator as it goes down. That discussion is in the help file, and there's a full discussion on it in the help file about cable elevators regenerating and needing offsetting loads.
All right, second question. What is the difference between a step and a group?
So basically the steps follow the convention that a lot of the manufacturers use, in that all the loads you put in that step are going to start concurrently, start at the same time. And after years of experience in the industry, you find that most people using sizing programs spend a lot of time constantly breaking those steps apart, not to create an overly false condition. The reality is most applications don't control the sequencing of the loads. They naturally sequence in the building. So we just made it easier for everyone to enter loads by creating groups of loads, like a bucket of loads, in which we changed the assumption. Instead of starting concurrently in that group, they will start through natural sequencing, one at a time, with the largest load coming on last. We think that fits the real world scenario of the way loads typically come on in the real world. If your loads are highly controlled and the sequence is highly controlled, you can always enter them in the steps based on concurrent starting in each step. So that feature's still there, but we think most of the time the groups are a better option.
What is the recommended minimum delay between steps?
Typically, you're looking at the recovery time of the engine generator. So in the real world, that happens naturally as loads just sequence on. If you're actually controlling it with some plant automation or some process control, usually a couple seconds, 2-3 seconds, you're just looking for the engine to recover from its frequency dip, which usually depending on the size of the dip, could be anywhere from a half second to 3-4 seconds. If you're taking less than 25% load hits, that recovery is probably less than a second.
How do we control motor start sequence?
Motor start sequence can be manually with plant automation sequence, but again, in the real world, most of the time it's done through natural sequencing. The motor loads start based on temperatures, pressures, levels, or human intervention starting them. So when you pick up a building, the motor loads are going to naturally sequence based on, how that facility just normally operates.
How does the program address uploads?
Uploads.
Your UPS loads, I'm sorry.
UPS loads. There are load types in the program for UPS loads. There's basically 3 main types of UPS capabilities: passive, line interactive, and double conversion. The passive, there's a big assumption of large amounts of harmonics associated with them. So usually we will set the voltage harmonic capability to single phase and crank the harmonics way up. Line interactive UPSs have very tight frequency tolerances, and those are programmed into the sizing software. And then double conversion. Double conversion UPSs to us are basically just a rectifier on the input stage. So we just need to know if it's filtered or harmonically mitigated or not. There's settings for that. And then you can also tweak the battery recharge rate. There's also an option for load level. So if you're not loading the UPS or not designing for full load on the UPS, you can actually adjust the load level on the double conversion UPSs.
If you have 3 steps, will you need 3 transfer switches?
The steps in the transfer switches aren't necessarily connected in any way. Transfer switches have to do with more the number of services or separate circuits that you're running in the building. On any given circuit or any given service, you could have any sort of load sequencing going on. I do see a question about motor codes. The typical code we default to is a code G, mid code G, which is ×6. That's if the motors are set to NEMA. If you switch over to IEC, the motor starting codes will jump up substantially. So for instance, the motor I was using, a 100 horse motor, would jump from a 600% start to an 850% start by simply switching it to IEC, which tends to be a European motor, which tends to have higher starting currents.
Is Power Design Pro capable of sizing parallel gensets?
Yes, actually, Power Design Pro has the ability to select the size unit and number of units. And that's a very good option for a lot of projects in terms of adding some scalability and redundancy to your project. We also find that typically mid-range diesel products in that 400, 500, 600 kW range with upsize alternators oftentimes will give you a little better performance in SKVA than maybe a large genset with an upsized alternator. You can see the combined effect of all the gens working together there.
Does Generac have any specific load types for air conditioning equipment?
We do have a special load type for HVAC equipment. In there, we typically use that in the early exploratory phases. You're always better served by entering HVAC equipment as their respective motor loads. But when you have limited information on the front end, we allow you to enter a tonnage and then the number of motors associated with that tonnage. For instance, a typical 25-ton unit has 2 compressor motors. So we assume that 25 tons is really about 2 12.5 horse motors. And the program also for HVAC loads has an option for reheat, in which you can add dehumidification load in with it as well.
All right, I do see that it is 12 o'clock here. So if you need to leave, feel free to go step off at this time. I want to let you know you will be getting an exit survey as you leave the webinar. Please go ahead and fill that survey in. To remind you again, you will be getting a link to the recording of this webinar, as well as a link to Power Design Pro tomorrow in an email. And we're going to stay on to answer all of the questions here. If you need to leave again, thank you for joining us today. All right, next question I have. How do I get access to Power Design Pro? Is it free to use?
Yep, it's on our corporate website. So you simply have to Google up Generac Power Design Pro and the link will be right there, and click on Try Me and it'll load right up. First time you'll click on it, you'll have to register, but then it drops a cookie so you don't really have to even have to log in after that. You can take you right to your projects from your laptop.
Is it possible to do cable sizing for a given generator on Power Design Pro?
That's a feature that's not currently in Power Design Pro, though we are creating, I know we're sitting here with Laura from our marketing group, and we're working on a little slider tool that will do cable sizing. It's kind of a little amp selector tool. It'll also do conduit fill and fuel consumption on the engines.
If step, concurrent mode, and group mode have the same sizing result, what's the reason to have two options?
If step, concurrent mode, and group mode, actually, they will typically give you different results. Starting everything concurrently will force a much bigger generator. Basically assumes all the motors are hitting at the exact same time and all their SKVA are additive. If we put them in a group, we assume natural sequencing, and we just have to be able to start the biggest one last. So it can result in a fair bit smaller generator, especially the alternator end for the voltage stiffness.
What is the lowest recommended running load to avoid wet stacking the generator?
NFPA 110 kind of sets that number at about 30%, and that's kind of an industry norm. So keeping your loads running at and above 30% usually keeps you out of trouble. If you find that you can't get to 30% load, annual load banking is recommended, just to kind of clean up the exhaust system and put some load on the engine.
Does the cable elevator selection figure in the regenerative voltage possible?
Yeah, we had that one a little earlier. Regenerative voltage is not taken into account. The program in the help file discusses that you have to have offsetting loads. So for a typical 40 horsepower elevator motor, you need about 30 kilowatts of offsetting load just to burn that power away. Usually that's done through the emergency system, but if you're totally isolated on the generator, then you're looking to add a load bank to the generator to offset that regeneration, or you're looking for the elevator controller to have a braking resistor. The trend we're seeing is that it seems to be away from braking resistors to IGBT regenerative drives, which means we're going to get regeneration back at the genset.
Here's a more specific example here. It says, I am using generators to provide standby power to 400 horsepower VFDs. What are the considerations that need to be evaluated?
The biggest consideration with the VFDs is the harmonics. If you have IGBT front ends on those VFDs, the harmonics are going to be low. In that particular case, the generators are simply getting the kW loading of the VFDs. If they're industrial 6-pulse unfiltered, you end up with a very significantly upsized alternator to handle the harmonics. So we would suggest looking at some mitigation of the VFD's harmonics, whether that's bringing in, if it's new, speccing a low harmonic configuration, or if they're existing, bringing in a power quality person to look at adding a filter to the front of that VFD.
Is there an option for transformer loads?
Transformers within most power systems typically end up becoming unseen, in that when the transfer switch closes in and energizes the building, in that period of time that you're going from no voltage to supplying voltage to the building, you're also picking up the transformers and energizing the transformers in the building. When transformers need to be looked at a little more closely is if you're carrying a bunch of loads and then you bring on a circuit later that is got a big transformer and it's going to be drawing some inrush. When you do that, that inrush then of energizing that transformer while carrying the loads is going to cause a voltage dip and be seen by the loads you're currently carrying. Most of the time, in most applications, it's a non-issue because you're picking up the transformers as you're picking up the building, and it's pretty much a non-issue. There are some unique cases where you need to look at it and you need to model how much kVA the transformer is going to draw because it's going to pull the voltage down while you're carrying the other loads. That is not something that we model in Power Design Pro because the kVA the transformer is going to draw is largely dependent on how far it is from the source. The impedance of the power conductors are going to mitigate some of that inrush current at the transformer.
Do the groups address multiple ATSs on the same generator system?
Again, groups and steps for Power Design Pro or any of the sizing programs out there aren't tied to the transfer switches. Transfer switches and application could have one service entrance rated transfer switch, and the loads could be sequenced underneath them, or you could have multiple transfer switches. But when a given transfer switch transfers into a circuit, that circuit is dead and needs to come back to life. So just because a transfer switch switches on doesn't mean you pick up the load immediately on that circuit. That circuit has to re-energize, and those controls and functions need to be brought back to life.
Does Power Design Pro cover biofuel?
Power Design Pro has a complete line. It has all of the generators that Generac manufactures in the lineup. So the biofuel products are under the diesel category, but you have to change the group, the load type. I'm sorry, the generator selection from the product family for diesel to the biofuel product family. So there are biofuels in there, also dual fuel. So all of the natural gas generators, propane and dual fuel and biofuel are all loaded in Power Design Pro.
How do you normally size overcurrent protection for a particular genset?
The overcurrent protection on the generator is normally set up to between 100 to 125% of the output of the generator if there's a single output breaker. A lot of times generators are seeing multiple output breakers, and in that case the breakers on the generator are sized to protect the various circuits they're feeding. You may have one breaker for the emergency system transfer switch, one for optional standby, one for fire pump. Then the breakers are sized typically to match the circuits they're connected to.
All right. How do you model a load in Power Design Pro that may have unique characteristics outside of motors and drivers?
So Power Design Pro does have a feature called miscellaneous. In the miscellaneous category, you can define the inrush current of a load. It's SKVA and its running requirements independently. So you can model a load's transient capabilities, running characteristics, as well as its harmonic characteristics. So the miscellaneous category allows you to really kind of configure and match any load type you may have just by mixing and matching transient, running, and harmonic characteristics.
Is it okay to load the generator to 90% running load?
So when sizing a generator, the ISO requirements are that in a 24-hour period, the average effective load on the generator needs to be 70%. What we find is there's transient periods or peak loading periods in every power system where you may go up to 80, 90% load when you get to your worst case situation. But typically peak demand or worst case is quite a bit different from typical. So the generators are sized that they can handle 100% of their standby rating, but the ISO standards for sizing generators require that in a 24-hour period, the average load has to be 70% of that standby rating. And that's not Generac specifics requirements, that's the ISO standards for generators in general.
Can you size medium voltage generators and simulate transformer inrush currents on low voltage generators magnetizing transformers?
The magnetizing of the transformer, we do this actually a lot. We'll use our integrated paralleling system, our MPS approach, and we'll take like 3/500ths and feed a step-up transformer, and then from that step-up transformer feed a number of loads. In that particular case, when the first generator closes its paralleling switch onto the bus, it's going to look like a huge motor start or almost a short circuit. So we'll get a very big voltage dip for maybe a second while it first closes in because it's energizing that transformer. After it energizes that transformer, all of the other units will parallel to it, and the low and the transformer becomes transparent to the system at that point. So there's really no need to model it, because when we first energize the transformer, we're going to pick it up, and after that it becomes, for the most part, not visible in the system, in that the generators have already energized the transformer.
Is the generator capable of absorbing any regeneration?
The regeneration capability of a genset's about, for a diesel, well, for all generators, it's somewhere in about the 10 to 15% range. So that's why we don't want to rely on the generator as, quote unquote, a braking resistor on a regenerative application. We want that regenerative power to be burnt off and not rely on the genset to be a braking resistor. If you apply too much reverse power to a generator, you're going to get an overspeed shutdown, which is going to be an undesirable result. But as a general rule, somewhere in that 10 to 15% range. After that, you're going to start accelerating the genset.
Is there a way to increase the horsepower available on the genset if a remote cooling fan is used?
Typically, the answer would be no, because you're going to have to power the remote cooling fan, and you can't rely on the utility to power the cooling fan because the generator's that power source. So the remote cooling fan is going to be normally on the emergency circuit or on the generator circuit. So in some ways, you've even cost yourself potentially some extra load, because you have some inefficiencies in the motor driving the cooling fan. And even if you put a VFD on that fan, at low cooling requirements, you'd probably save a little power, but at maximum load, you're not, because you're going to have maximum fan speed at maximum load.
All right, we're going to do our last question here. Can you adjust the ATS time delay transfer?
Transfer switches can have a delay put in them. Almost all transfer switches in the market will have a feature called genset warm-up, and you can use that time to just sequence some switches, just to put a few seconds between them coming on. In most applications, you're finding whether one transfer switch kicks on or whether 3 or 4 kick on, the situation to the loads isn't much different. The loads were all dead, no voltage, generator kicks on, transfer switches kick over, you go through a transient phase, but then the loads are powered. So whether I do that one at a time as transfer switches or throw them all at the same time, the end result to the loads are very similar.
Thank you, Michael. This has been very informative. I want to remind you, as you exit the webinar today, you will get an exit survey. Please go ahead and fill your answers in there. And again, tomorrow you will receive a link to the recording of this webinar, as well as a link to Power Design Pro. Thank you so much for joining us today, and have a wonderful rest of your Halloween.